Hello everyone, I'm Justin Goodman, this is Mark Moore, and our project is evaluating the role of audio in comprehensive video understanding. We worked in Dr. Chenliang Xu's lab with Yapeng Tian, both of who have done just outstanding research in computer vision. So this summer, we collected 3 different video data sets. The first is an expansion of Yapeng's audiovisual event data set. The second is a subset of the first, but annotates the spatial locations of each audiovisual event. And the third contains 2 audio-based captions and 2 video-based captions for each video.
So most datasets contain descriptions from animators that can see and hear the video, and we suspect that this influences how they describe video and audio. So perhaps a better model can be developed using a dataset that focuses on sight and sound individually. We propose a novel dataset to explore this. So computer vision is one of the hardest problems in AI, but considering its applications, we think it's important to have a better understanding. Our colleague Chen Xiao will discuss a possible model that could use our dataset to help further our understanding.
Hello, everybody. My name is Shiva Lakshmanan. I work with Professor Gaurav Ghoshal this summer, and my research project is on investigating human mobility in virtual and physical space. Human mobility in this context is just looking at how people move across these 2 domains. So when you think about how people move in physical space, you have to look at things like traffic, weather, and cost. But if you look at people moving on virtual space, all you need is a high-speed connection. So you think these 2 realms are different, but they're actually same when you look at how humans move across these 2 domains. So what I did is why I wanted to explore that further. So I looked at 3 different metrics of human mobility, and I saw that across both domains, they are the same. And the next thing I did, I created a model to model the number of location website discoveries as a function of total location websites discovered. And that also was the same. So why is this important? If 2 seemingly different realms of human mobility are different, but we actually see that they are the same, is there some overall principle of human dynamics? And can learning about one help you learn about the other? Thank you.
Hello, everyone. My name is Connor Luckett, and this is on the socioeconomic and structural dimensions of urban mobility inequality, which is a lot to say. We look at how people move from point A to point B, and we also take into account their income. So there's this question on the minds of a lot of people. Are the wealthy better off than the poor? And what way? So one of the ways we can think about this is their access to goods and amenities, and this is sincerely important because education and access to education is one of those primary factors in determining social mobility, moving from one class to the other. But when we think about how we move within a city, we're restricted when we drive to a city's street network. So we have to take that into account of our new idea of distance. So the approach is fairly simple. Have you ever gotten directions on Google Maps? It's a lot like that, but we do it about 1,000 upon thousands of times over and over again, and we always start at the centroid of a zip code. That's how we're breaking these barriers, by classifying by economic zip codes. Then we always route to nearby amenities, and then we calculate what's called a detour factor, which is just a measure of how far out of the way we have to go to get to that destination. And what we found is really interesting because ultimately it varies from city to city because every city structure is different. But look at Rochester's income gap, and as a whole we saw this trend as a mobility advantage for the poor. However, Boston was the exception to this rule. So if you'd like to learn more about mobility inequality, come see my poster. Thank you.
Hello everyone, I'm Koe Kadoma. I am joined with Sam Lowenstein and Michael Peyman, and under Dr. Gnjatovic, we investigated audio-based non-invasive blood pressure estimation, which is really just a fancy term meaning we wanted a smartwatch which can read blood pressure. Why does anyone care? Well, there are currently activity trackers and smartwatches which can read heart rate, but blood pressure is a key indicator of heart health, and as you can see, heart disease is the leading cause of death. So if you're constantly monitoring your blood pressure, you're constantly monitoring your heart health.
We wanted to know how we could hear blood flow and relate it to other heart data. And since we weren't able to test on ourselves, we made a phantom forearm and connected it to a mock circulatory system at the Med Center. Then we placed transducers on the forearm and collected waveform data with an oscilloscope. This data was then fed into a neural network, and we tried to find a relationship between the waveform data and pressure readings.
Our project is interdisciplinary, combining computer science and electrical engineering to create a biomedical device. It has the potential to revolutionize healthcare by early detection and prevention of heart disease, leading to longer, healthier lives. Thank you.
Hello, everyone. My name is Alexander Berry. My project is bias-free machine judgment for job interviews. I worked in the Rochester Human-Computer Interaction Laboratory. And this project is predicated on the idea that in the future, all job interviews will be done via video and assessed by machines. And the motivation is that traditional human interviews are subject to bias. And if we're going to transition to this machine method, we need to make sure that the bias is as little as possible. And we want to know what applicants can do to improve their standing in job interviews when transitioning to this new model. So our goals were to extract audiovisual and linguistic features from a data set and categorize participants by their age, gender, and ethnicity. We compared the distribution of scores and trained linear logistic regression models and studied the features with the greatest coefficient magnitudes. And so our results show that there really wasn't any bias in terms of age or gender, which is consistent with previous studies. To improve their hiring score, interviewees should use fewer negations, filler words, and words with negative connotations, and vary their smiles. So hopefully this will be the groundwork for future projects which can create more accurate prediction models. So if you're interested in more, please see my poster. Thank you.
Hi everyone, my name is Nicole Gates. I'm from Wellesley College, and my project is using speech analysis to determine the presence of Parkinson's disease. I worked in the Human Computation Interactions Lab, I said that wrong, whatever, and I worked with Dr. Asan Hawk. So one of the questions that I wanted to answer was, what if you could detect the presence of Parkinson's disease just through your voice alone? And what if you could do that without actually leaving your house? So for my task, I focused on the assessment of Parkinson's disease that used audio tasks. Task 1 is shown up there with that sentence that the people say, as well as task 6, which is a sustained phonation of ah. And using those, I was able to extract features from those phonations and determine whether they had any correlation with PD or not. So digitizing the assessment is one thing, but the analysis is quite another, and that's what I was focused on. So mostly I was focused on which features specifically had higher correlation with PD and which ones had lower correlation with PD. And this is important because, as you can see from the figure there, an estimated 14.2 people will have PD by 2040. So this is somewhat of a pandemic, and if we can find a way to make this process easier and faster and less stressful for patients, that'll be better for everyone. If you have any questions or are interested in my research, please come visit my poster. I'd be happy to talk to you about it. Thank you.
Hi, I'm Eric Azzarano, and as part of the Music, Media, and Minds REU program, I worked on developing a framework for creating music-generated games. Inspiration for the project came from the fact that I like to listen to music while playing video games, but I wanted to learn more about cases where games are actually generated by music. And what I mean by music-generated games are games where the mechanics react to music or sounds in the games rather than the other way around like most cases. So in order to build a framework for generating this type of game, I gathered different information about game mechanics, audio features, and how they should relate to each other in the context of a game. And then using this framework, I was able to build a prototype game. It's an arcade-like shoot 'em up that's created by music. To play it, all you have to do is stream audio from sites like Spotify or YouTube, or you can play a song from your own music library. And I'll have a demo of it set up at my poster, so be sure to stop by, check it out, and try it with a song that you like. And overall, the framework that I propose and the prototype that I built should provide a base for future experiments dealing with music-generated games, especially for the need of human subjects. And ultimately, my goal is just to provide insight into an innovative game genre that's largely unexplored in research and in the game industry. Thank you.
How would it sound if Mozart covered Jingle Bells? This is a problem of musical style transfer that I explored this summer, taking the style of one musical piece and applying it to another. The problem with musical style is that it's difficult to define. Everything from rhythm to texture to motifs contribute to the musical style of a piece. So I focused on a single aspect, harmony. This is a lead sheet. It contains a notated melody line with chord progressions that represent the harmonic style of a piece. And to build my model, I used the Wikiphonia dataset, a collection of 6,500 lead sheets of musical pieces in genres from Hungarian folk music to bossa nova. And the model I built is a variation of a machine learning model called an autoencoder to learn the harmony-melody relationships in my dataset, and also to produce style-appropriate harmony given any melody line. The model essentially learns to produce and interpret a latent vector, which is a mathematical representation of the harmonic style of a piece. My research can be used to integrate different styles into compositions or explore the harmonic differences between genres. And ultimately, this kind of research gives us a better computational understanding of music, which is important for creative human-computer collaborations. And if you want to hear an example of musical style transfer, I have a demo set up on my poster, number 17. Thank you.
So I came in knowing that I was interested in doing research and that I wanted to do research for the rest of my life. But not necessarily knowing what it would be like to spend my entire day just working on research, since I've only done research during the year. And also not knowing what grad school would be like, what the type of advisor-advisee relationship was like, what I was getting into with the application process, and I think that's really where the program stood out for me. Maybe the non-research aspect specifically, but just the idea of doing research day to day, and also finding out what the grad school application would look like, what life as a grad student is like, what to look out for the next 5 years of my life when I'm spending all of my time kind of banging my head against a problem. So I think in that regard, I really, really enjoyed my time here. Honestly, it was a bit too short. We only had 9 weeks for my research program. But would I do it again, and would I recommend it? Yes, I would. If this is what I got to do all day and didn't have to take any classes during the semester, that would be perfect. That would be ideal. Probably why I'm going to become a grad student, because class is kind of something that interferes with the research process, just because I have it every day. And so yeah, I realized, obviously this is not quite what grad school is like. You have classes, you have a lot more pressure, you're working more long-term on longer-term problems. But the idea of just sitting down, working on something, getting stuck, barreling past it, but this being the main thing that you do, research, I didn't come in with set expectations, but it exceeded them if they existed. This is what I would do, yeah. If it's another person who's interested in applying and they're like, okay, what was it like? I would say, you come in, you have a problem and you're trying to work on it, and the 9 weeks kind of just fly by. What's nice about it is that you have the Kearns Center supporting you. There are lots of events going on. And I think it would be a good, valuable experience for someone who's interested in doing this type of research, like long term.